All right. Hello, everybody. It's still Friday. Again, I'm doubling up this week on lectures in preparation for next week and the following week. But I wanted to go ahead and get this knocked out today. We are still studying 2-1 and 3-1. If you've been in live class this week or this past week, you know that we are beginning earthquakes and this heavy material, and we really, really, really have to make sure that we get a good foundation in this stuff before we start triangulating and learning how to find the epicenter of an earthquake. So, still 2-1, talking about those internal processes, and then 3-1 still. We can actually throw 1-5 in there as well, the movement of Earth's crust. But 3-1 and how that influences human activity. How does that affect us on the surface? Okay. In class, we'll review with the time to climb. Today, we are talking about waves, and this is something that is super, I guess, close to my heart. I enjoy talking about waves, but I find that it is something that's very challenging for students. And so, at any point during this lecture, please start writing down some questions for me, some things that you don't understand, and we will walk through those things in live class. Okay, so again, we don't have a large foundation in this information before we start high school, and so that makes it kind of difficult. And then also, we talk about this material in several other aspects. We talk about this material in space a little bit. In other classes, other science classes, you're going to talk about sound. And so this is like physics, for example. This is good foundational information for some of the other things that we're going to study in this class and then beyond. So getting into it, let's talk about waves now. When somebody mentions waves, most of us probably think about like an ocean wave. That's maybe our only kind of real tangible experience with big time waves, right? Or if you're like me, out on the lake and your mom slings you halfway across the lake on a tube, you might have some experience with waves as well. But waves have some properties and behaviors that we're going to discuss across all waves. And there are so many. Waves affect so many aspects of our lives. It's not even funny. Um, However, we're just going to be talking about earthquake waves, but I do have to give you some foundational information, and that's what we're doing today. Okay. You do need to know what a medium is. So like if I say, what is your if you're an artist, what is your medium in art? Do you do sculpting? Do you do paints? Do you do pastels? Well, what is your medium? Do you do pottery? Okay. That is whatever you are using, the material that you are using. If I ask you if you're a musician, I ask you, what's your medium? You might say the French horn or a clarinet, a trumpet, or to go string side of that, a violin, or could be drums, something like that. So that would be your medium. If you ask a baseball player, soccer player, what their medium would be, it'd be whatever they're using, right? It's whatever material that is being used for that task. So what we're talking about here, a medium is going to be any solid, liquid, or gas that a wave can travel through. Okay. And it is true that waves travel at different speeds through these different mediums. Okay. I'm going to get way more into that when we talk about space. But I don't know if you've ever experienced an earthquake. I know I experienced an earthquake only one time, and it was like we were in Spartanburg, living in Spartanburg, and my husband and I were sitting there in the evening after the kids had gone to bed. We were watching a TV show, and all of a sudden, it was just like a just a little jolt, like a kind of feeling, and I was like, "That was weird." And I almost didn't want to say anything to my husband. He was like, "That was. Did you feel that?" And I was like, "Yeah." And so we looked it up, and sure enough, there had been an earthquake, a small one, obviously, that occurred in our area. So I haven't felt a big one, but a little shake in Spartanburg. There was definitely some activity in that Boiling Springs area. This reason it's called Boiling Springs. Um, how do you think waves from an earthquake move differently at the surface versus internal Earth? That's going to be a really underlying question. Okay, you're going to learn a lot today. I told you I prefaced this whole unit when we were talking about layers of the Earth about how do we know what's down there? How do we know? We talked about this in the last lecture. How do we know what's down there? If Wegener had to have all that evidence to establish that for him continental drift, but eventually plate tectonics was real, and we can't even dig through the crust, what kind of evidence could we possibly have to know what's below the surface of Earth? Keep that in mind. All right, waves. There are two categories of waves. One, the electromagnetic waves, electromagnetic radiation, the electromagnetic spectrum, anywhere from microwaves all the way up to gamma radiation. Um, these waves we're going to kind of like pick out and set aside because we are going to talk about them again. We're going to especially talk about them when we talk about technology in space and how we read what's coming from distant stars and different galaxies. Okay. So, again, you're not responsible for this information yet. Good to know, though, electromagnetic waves, they can move without a medium. They can use a medium, but they can also move in like the vacuum of space. All right. And the example that we're really going to talk about here is light, okay, and radiation. We're really going to talk about that a lot with solar radiation in the next unit, Unit 4, with the atmosphere. So again, putting that one to the side. What are we really discussing here with seismic activity? What's happening? These are mechanical waves. Mechanical meaning something is actually moving. Energy is being transferred in the form of vibrations. And the molecules of those solids, liquids, and gases that we're talking about, the medium, the molecules of those mediums are moving. They are vibrating to transfer that energy from one place to another. Okay. Examples that we have here, sound is an example. Everybody's like, well, sound travels on nothing. No, that's actually not true. If sound didn't need a medium, we would be able to hear sound in space, which we cannot. Okay, you cannot hear sounds in space because there is no medium for sound to travel on. It is a vacuum. All right. Sound, just like if you were standing in front of me, sound travels from my mouth to your ear by compression and rarefaction of the molecules. And if you can see me in the camera, that is pushing together and pulling apart of the air molecules. Okay. And that's how sound has to move. It cannot move transversely, which is up and down. So sound moves across the molecules of the air. All right. So that is a gas by pulling those molecules together and pushing them apart. Another example, clear example here is seismic activity. And I kind of, you're like, why do we need to know about sound? Well, because one of the seismic waves moves exactly like sound waves. And so that's really important. And another type of seismic wave moves up and down in the opposite direction, which would be the opposite of what sound does. It moves more transversely like light. And so those are good concepts to come back to. All right. All right, all waves, no matter if they are classified as electromagnetic, if they're on the electromagnetic spectrum, or if they are mechanical in nature, all waves have the same behaviors and the same properties, okay? The properties, those are our measurable things, like wavelength. We can measure from crest to crest or trough to trough, which we can talk about later. Um, or frequency. How frequent does it occur? If it occurs a lot, that means it's higher energy. That means it's more dangerous. Okay. And then we have amplitude. I don't know if you've ever heard, somebody driving down the road, or maybe it's you guys driving down the road and you got those big speakers in the back and it's bomb, 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 and it's shaking the windows and rattling everything in your house. That thing in the back of the car is called an amplifier. So you can think about this as it is turning up the energy in that wave. If it's sound, for example, it would be turning up the volume. Okay. If it's light, for example, you would be making the light brighter. So amplifying. And then we have speed. And that one is very important to what we are studying right now. Speed, of course, is distance divided by time, the distance that wave traveled in a given amount of time. We'll talk about that in just a minute. Behaviors. How do all of these waves behave? Okay, what are their actions? How do they interact with their surroundings? They can reflect, so they could bounce. All right, we're going to talk about that in just a second. We talk about interior Earth, especially like um, the outer core and which one of these waves doesn't interact with it. Refract means to bend. Okay, just like if you had a straw in a glass of water, if you look at a straw in a glass of water from the side, you may see that it looks bent or broken. And that's because the light that is encountering that object is moving through different mediums. Okay, it's moving through the air, which means it's moving pretty quickly. It hits that glass, which is, of course, a solid. Okay, and then it enters the water again, and then it exits the water, it exits the glass, it goes back out into into the air. And each time it changes the mediums, it slows down, and you get this warped look. It's why things, if you drop something at the bottom of a pool and you go down to try to get it back, it's going to be in a different place than what you thought it was because of refraction. Absorption, meaning like sound, it being absorbed. If you have experienced band or orchestra, they may have those things all the way around the band room, the orchestra room, that absorb sound to bring in. And the opposite of absorption would be transmission. What is allowed through? Okay. So the same properties and same behaviors we're going to talk about multiple times throughout this class. The two main properties that we'll look at the most for earthquake waves is speed and wavelength. All right. Scientists measure wavelength based on the type of wave that it is. So here we can see that we have this transverse wave, okay, up, down, up, down, up, down, okay? And the top up here we called the crest, right? That makes sense. If you were on a little bicycle, you might say, I had just crested the hill when I saw whatever, Bigfoot, who knows? Then the other one is called a trough. And anytime you have that U shape right there, just like a pig eats out of a trough, the reason it eats out of a trough is because it has a flat nose. So if it has, corners, it's not going to be able to get to it. So a trough for a pig is U-shaped so the pig can consume all that slop, right? So the trough down here, and I know it's spelled weird, and if you guys know me, I'm a horrible speller. Okay, but trough is the word there, and that's the bottom part of that wave. So crest being the top part of the wave, and trough being the bottom. Cresty. Wow. All right. Crest is the top, trough is the bottom. And again, transverse wave, like light, moves up and down, up and down, up and down. A longitudinal wave, what do you see in that word? What do you hear in that word? I hear long. A longitudinal, long wave. It's like taking a slinky and pulling it taut, and then you release some of the rungs at one side, and it kind of wah, 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 back and forth, okay? That's called compression and rarefaction. And you can see we have compression zones here. And this says expansion. The word is rarefaction. So we have places where it comes together and places where it pulls apart. That is how sound works. That's why I brought up sound at the start of this lecture. That's how sound works, by pulling together the molecules and pushing them apart, and that it trades the energy off by doing so with the next group of molecules. All right, seismic waves. Seismologists study these seismic waves, seismic activity all around the globe. We talked about a couple lectures ago in the Cold War how nations put out all kinds of seismographs across the world to basically find out who was testing atomic bombs, right? And what it did was it really helped scientists map out the boundaries of plates because it gave so much more data than we originally had. So across the globe, seismic activity is monitored daily, hourly, minutes. Okay, if you pulled up that USGS website from the last lecture and the lecture before that, then you notice it changes almost every 30 seconds. Okay, whenever something new pops up, how do we have that data? How do we, as laymen, right, just normal people, how do we have access to that data so quickly? Okay, because these seismographs are all over the world. Seismic waves move out in all directions from a point called the focus. That's so important. We learned that last class. I need y'all to understand that it moves out from every point. Every point. Kids want to really kind of be like, well, it only moves in this direction. No, it breaks and moves out from every point of that break. Okay. There are two types of seismic waves. We have classifications of surface waves. Those are the ones that are most dangerous to us. Those are the ones that only travel across the surface or across the crust, across the lithospheric plates, all right? They do not enter interior Earth. And then we have the body waves, this is what makes this material difficult. We have primary waves, which you can imagine, primary means first, right? It's released first from the focus. And we have the secondary, which is released second. And going back to what we learned last class, the anatomy of the earthquake, the focus is the exact point of that break. All right, the exact point of the break is the focus, and all activity is released from that point, from that break. Okay, I do want you to, you're going to fill this out in the notes. I'm not going to do it with you here. I'm not going to show you the answers either. You go back and change it or get it right from the lecture. But this is a slide you'll need to screenshot and save in your Unit 3 folder as your study guide for this unit. And this is one that you're going to want to study, okay? This is truncated as much as I possibly can make it. It's as simple as I can make it. This is the absolute most essential information that you need about primary waves, okay? First, primary means first. It is the fastest. It's the very first wave that is released from the focus, and it comes out the fastest and travels, okay? It can move through all mediums, solids and liquids. Here, that's what we're talking about because internal Earth, right? So it can move through every single layer of the Earth. That is so important. Remember, I said, how do we know what's down there? Why do we think we have enough evidence to even have a theory on this? These are long waves. They're longitudinal, all right? You want to know why I talked about sound? Here's why. They move by compression and rarefaction. So get my little pen going up here. All right, so you can see the pulling together and then here the pulling apart. So again, that if you can imagine that slinky, put that slinky in your head, right? If you pull just one of those little, I don't even know what you call coils, I guess, it sends energy going throughout each of those coils. But the only way it can do that is by pulling them together and pulling them apart at other points. And then it moves kind of like a snake, if you could imagine that. Like, or if you're a biology person, maybe Paracelsus of the esophagus, or I think the small intestine does as well. If you love that science, that would be a good example there. So compression and rarefaction. Take that off of there so it's not there in class. So it moves, you might see it as push together, pull apart. You might see it as it moves side to side, okay? But really we want that vocabulary, we want that scientific vocabulary, compression and rarefaction, compressing and rarefaction. The secondary waves, you guessed it, are released second, which means they are slower than the P waves. They can only move through solids, but this gets kids confused, okay? What that means when I say it can only move through solids is that it cannot move through pure liquid. So be careful with that. So if you're thinking in your head, you're like, oh, she told me at the start of this lesson to be thinking about our evidence for what's in interior Earth. Okay, that pure liquid there gives you a heads up about where we're going with this. What layer is pure liquid? Okay. It moves transversely. A secondary wave moves transversely, which means up and down. Again, going back to our just crested the hill, or a pig eats out of a trough. Crest and trough, up and down, up and down. And when this is the easiest one for students to understand because this is what we experience. If you drop a rock in a pond or a body of water of some sort, whatever, you know, that ripple effect is a transverse wave. It's what we experience when we go to the beach. That is a transverse wave. And so, and even when we talk about light, all the electromagnetic spectrum moves transversely, up, down, up, down. Okay. Again, that's another verbiage you'll see, up, down, up, down. Okay. But I want you to know scientific crest and trough, crest and trough. All right, let's get to it. We've been talking about this for a while, okay? The mantle, why is it so confusing that S waves can only move through solids? Well, because when you think about the mantle, you think about mantle, you kind of classify that in your head as a liquid, but it's not. It's very viscous, meaning it's just as you would imagine that slow moving magma to be, right? And so it's not quite solid, but it's not quite liquid. And so for this reason, the S waves can travel through the mantle. All right, they can travel through the mantle, but I want you to look right here. Where do they stop? Where do they stop? We have a shadow zone. Where do they stop? Okay. So all of this down here does not experience the S wave. We cannot determine the S wave from that point. All right. And the reason is because there is pure liquid in the core. And that's what tells us that. Well, the S wave can't travel through it. So we know it must be pure liquid because that's what the S wave cannot travel through. Okay. If that's confusing, bring that question to me to class. The P wave can travel through all material. It can travel through all material. We are not going to get into why it has a shadow zone because that is well beyond where we need to go for our standards. Okay, it does have a shadow zone. Okay, that's all you really need to know. We can talk about reflection and refraction at another date. Maybe when you go to college to become a seismologist, that's where you'll get that information. But the P wave, as you can see, can travel from here and straight across the earth. It can travel through any of that material. All right. So to note, this is what helps us with that theory that the outer core is pure liquid metal. These questions are super important. I'm gonna go through a couple of them. We're gonna do this in class, obviously, but P waves can travel through all of Earth's layers. We just found out that to be true. Oh wait, that one. I bet. There we go. S waves can travel through all of Earth's layers except the outer core. We just found that to be true. And then this one's so important. This gets kids confused. If the inner core is solid, that's what we thought, right? Inner core is solid. Why can't the S wave travel through it? Really want you to bring that question to me in class. Okay? What is preventing the S wave from getting to the inner core? All right, surface waves here. Surface waves, these are the most dangerous. Why? Because they're actually a combination wave. So the P wave gets there, the S wave's right behind it, and instead of this wave, if you're looking at my picture, instead of this wave going side to side and then up and down, it's actually going side to side and up and down at the same time. What is that? We're not going to talk about Raleigh or love waves. You're not responsible for that. The difference there. Okay. But really what it does is it creates this circular pattern of the material because it's going side to side and up and down. And this can cause the topsoil to liquefy, is the word, liquefaction, which means that things on the surface can just sink because the topsoil is going in complete circle. There's complete shamble of the top soil. Then things can just, especially large things like buildings, can just sink down into Earth's layers, right? Into Earth's crust. So surface wave, definitely the most detrimental. Again, we'd be all right at the surface, probably, if it was, here's the surface, if it was just the P wave and these waves were just going side to side, okay? We might be okay if it was just the up and down. But when you have the up and the side is a terrible example there. Let me clear that out. If you have these going up and down and side to side, erase, it's not working out. Then you get this motion right here. And of course, that can make for a very dangerous situation for humans on the surface. Okay, catastrophic event. All right. This is very important for my students. I am going to be looking at each one of your responses because this is not just did my students understand the vocabulary? This is not just did they get the concept? This one is can you now take that information and apply it? All right. So for my students, I'm really heavy looking at this discussion question. What does this knowledge, P and S waves, and the material they can travel through, tell us about interior Earth? To kind of form it a different direction, what does this information tell us about the consistency of each layer? How do we know? How do we have this theory? What does it give us? Okay, so I'm really heavy looking at this. Can you apply this information from the last two lectures? All right, guys, I hope you enjoyed it. I will see you next week. Have a good day.